All right, so now we're going to talk about what is known as the symplectic 2 form, which is a geometric invariant of Hamiltonian dynamics. Okay. All right, so the canonical symplectic form. Okay, is given by the following. So it's denoted by omega, and it's equal to sort of the qi wedge dpi. Okay, where again there's this implicit summation over I. It's like via the Einstein summation convention, right? So there's an implicit sort of summation, sort of over I, which is called the Einstein summation convention. Okay. All right. So the wedge product is basically a anti-symmetrization of the tensor product, if you will. It's like up to some scaling, so I can write down what it is explicitly. So it's dqi tensor product dpi minus dpi tensor product dqi. Okay. But I still have to explain to you what these dqi's and dpi's do, right? So where dpi and dqi are what are known as one forms, okay, which are linear functionals. On t star q, okay, with the property that they have these sort of Canonical delta-like properties, that if you take the pi, it's like applied to a vector, which is sort of in the qj direction, okay, that this is equal to 0, okay. And if you have the pi in the pj direction, right, this is the Canonical delta function, delta ij, which basically means that it's 1 if I is equal to j, and 0 if I is not equal to j. Okay, so it's more or less, it's like these things are like the canonical dual basis, if you will. It's like for the space involving q's and p's, okay, or these vectors on q's and p's. And then you have the qi, right, paired with the qj, right. Well, paired with a vector, it's like in the qj direction, is again a Canonical delta function, and then the qi paired with a vector in the pj direction, okay, is equal to 0. Okay, so this is the definition, if you will, of the one forms. It's like just defined in terms of linear functionals, right? So sorry, linear functional. Okay, so basically it's like you can define the action of a linear functional by just defining its action on a basis for the vector space, and that's what I've done here. Okay, so with that in mind, it's like then I can start asking, well, how does this symplectic form look like when you act it on an arbitrary pair of vectors? Okay, so what happens is that this is going to be what is called a 2 form, right? So it's going to be a bilinear functional. It's like on 2 vectors, okay? And then we'll see what happens. Okay, so with that, you get that omega, right, can be sort of, you can think of omega acting, it's like on a pair of vectors. And again, I'm going to use the Einstein summation convention here. So I'm going to suppress the summations. So you have an alpha j d qj term, right? So this is a vector in the sort of the positional directions, and then you have a vector which is in the momentum-like directions. Okay, that's one vector. And then there's another vector, it's like, which was coefficients I denote by tildes now. Okay, so these are two vectors. You can think of them as v and v tilde if you like. Okay, and then we have this expression for omega expressed in terms of tensor products. Okay, so the idea, of course, if you have a tensor product of two one forms, is that the first one form gets applied to the first vector, the second one form gets applied to the second vector, and you take the outputs and you multiply them. Okay, so that looks like the qi applied to alpha j dd qj plus beta j dd pj multiplied by the pi applied to alpha tilde j dd qj plus beta tilde j dd pj, right? So that gives you the first term, the qi tensor product, the pi acting on this pair of vectors, and then there's the second term where the sort of the q's and p's are swapped, right? So minus the pi, again, alpha j d qj plus beta j dd pj times the qi alpha j tilde dd qj plus beta j tilde dd pj. Okay, all right, so that's really just coming from the definition of the tensor product. Okay, and then what happens is that a lot of these terms vanish. It's like, because as you know, this delta qj, it's like vanishes on everything except for the part, it's like, which involves, it's like d dq, oh, sorry, d, okay, so d qi vanishes on everything except for the part which involves the vector sort of in the q5 direction, right? So this term, for example, just collapses to alpha I, okay? And then this term here collapses to beta I tilde, okay? All right, so this becomes, and again, there's this implicit summation, right? So this is alpha I, beta I tilde minus beta I alpha I tilde. Okay, so you can write this, it's like in the following way, okay, in terms of quadratic forms, expressed in terms of vector coefficients. Okay, so you can think of these two, again, these things as two separate vectors with coefficients alpha and beta, and alpha tilde and beta tilde. So I can put each of these coefficients into a long vector of length 2n. So I'll do that for this first piece. I'll have alpha 1 to alpha n, and then beta 1 to beta n. All right, so that's a row vector. And then I have some sort of matrix. And then I have a column vector which involves alpha tilde 1 to alpha tilde n, beta tilde 1 to beta tilde n. Okay? And then it turns out that the matrix, it's like, which pairs these two vectors together to give you this expression, looks like the following. You have a 0 n by n matrix, you have a n by n identity matrix, you have a minus n by n identity matrix, and you have the 0 matrix here, right? So this is, let me just put n by n there, n by n, where n is the dimension of the sort of the position variables, for example. Okay, and then this whole matrix is called the symplectic matrix, denoted by J. Okay. All right. So when you do that, then the following happens. Okay. So what basically happens then is that the symplectic matrix J is a representation of the symplectic form in the following sense. So the symplectic matrix J right, is the representation of the symplectic 2 form omega, right, as a mass matrix in a bilinear form. So what does that mean? That means then when you take the symplectic form omega, all right, and you pair it at two vectors, let's say v and v tilde, this is equal to v transpose j v. Okay, so on the one hand you have this two form or two differential form, and on the other hand you have this quadratic form in terms of a matrix J. Okay, so in any case, it's like you encode it. It's like the action of this two form on arbitrary vectors in terms of this J matrix in this sort of quadratic form or bilinear form representation. Okay, so so let me just stop here for now. It's like, and then the next thing we'll do is we'll see how this allows you to write down Hamilton's equations, Hamilton's canonical equations, in terms of the symplectic form, if you will.